Fixed length encodings work well when all the possible choices have the same information content. In other words, all the choices have an equal probability of occurring. If those choices don't have the same information content, we can do better. To see how, consider the expected length of an encoding, computed by considering each x sub I to be encoded and weighting the length of its encoding by p sub I, the probability of its occurrence. By doing better, we mean that we can find encodings that have a shorter expected length than a fixed length encoding. Ideally, we'd like the expected length of the encoding for the x sub I to match the entropy h of x, which is the expected information content. We know that if x sub I has a higher probability, in other words, a larger p sub I, that it has a smaller information content, so we'd like to use shorter encodings. If x sub I has a lower probability, then we'd use a longer encoding. So we'll be constructing encodings where the x sub I may have different length codes. We'll call these variable length encodings. Here's an example we've seen before. There are 4 possible choices to encode, A, B, C, and D, each with a specified probability. The table shows a suggested encoding where we follow the advice from the previous slide. High probability choices that convey little information, for example B, are given shorter encodings, while low probability choices that convey more information, for example C or D, are given longer encodings. Let's diagram this encoding as a binary tree. Since the symbols all appear as the leaves of the tree, we can see that the encoding is unambiguous. Let's try decoding the following encoded data. We'll use the tree as follows. Start at the root of the tree and use bits from the encoded data to traverse the tree as directed, stopping when we reach a leaf. Starting at the root, the first encoded bit is 0, which takes us down the left branch to the leaf B. So B is the first symbol of the decoded data. Starting at the root again, 1 takes us down the right branch. 0 the left branch from there, and 0 the left branch below that, arriving at the leaf C, the second symbol of the decoded data. Continuing on, 1, 1 gives us A, 0 decodes as B, 1, 1 gives us A again, and finally 1, 0, 1 gives us D. The entire decoded message is BCA, BAD. The expected length of this encoding is easy to compute. The length of A's encoding, 2 bits, times its probability, plus the length of B's encoding, 1 bit times a half, plus the contributions for C and D, each 3 times 1/12. This adds up to 1 2/3 bits. How did we do? If we'd used a fixed length encoding for our 4 possible symbols, we'd have needed 2 bits each. So we'd need 2,000 bits to encode 1,000 symbols. Using our variable length encoding, the expected length for 1,000 symbols would be 1,667. The lower bound on the number of bits needed to encode 1,000 symbols is 1,000 times the entropy h of x, which is 1,626 bits. So the variable length code got us closer to our goal, but not quite all the way there. Could another variable length encoding have done better? In general, it would be nice to have a systematic way to generate the best possible variable length code, and that's the subject of the next video.